Okay, good morning, good evening, good afternoon, everybody, depending on where you're joining us in the world and whether you're watching this live or after the fact as we are recording this. It's my great pleasure to introduce our next MechE Alliance seminar speaker, Dr. Albert Moussa, who is an esteemed alum from the Department of Mechanical Engineering, a founder of BlazeTech. BlazeTech was originally founded to perform research and development in the areas of fire and explosion. He's focused on combining theory and practice to bridge the gap, the valley of death, if you will, between industry and academia. He's worked on major problems in the chemical, utility, aerospace, defense industries with a broad set of experiences that brings us to here today. And he'll share his journey, but also share some of the exciting work that BlazeTech has done.
Okay, Brian,
thank you
for that nice introduction. I will talk today about bringing science engineering to safety. And what I'll talk about is first, how I got where I am after MIT. And Teresa and Brian asked me to do that. I guess this is my journey, so to speak. I'll talk about safety as a consulting practice. That's gonna be a general discussion. Then I'll talk about two specific examples of project at BlazeTech, where I'm going to show some of the technical work we do. They'll cover aircraft fuel tank explosion and explosion and toxic emission from hazardous chemicals. And then I'll share some thoughts on the starting of a consulting practice, the do's and the don'ts that I've learned the hard way. So how I got here, I got my PhD in '76 at MIT, and I was working on fire research. I was very interested in safety, and I tried to start a program on safety at MIT. I got Professor Ernie Carvalho, who was then Associate Dean of Engineering, interested, and he told me, formulate a program. And I identified many safety activities at MIT then. For example, Norm Rasmussen was a leader in nuclear safety, and Jay Fay in our department was doing liquefied natural gas safety. So I invited these various people, about 15 or 20 people in a large conference room around the table, so to speak, with Ernie Carvalho's sponsorship to describe the program. The main question was, is there a pot of money to support this someplace? And the answer was no. And that basically kind of killed the ideas. And I learned then that money really talks at MIT, as it does in many other places too. So a classmate of mine who's now at the Magnet Lab, he called me and said, you know, there's a company that describes very much your skills. You should apply there. That was Arthur D. Little Incorporated in Cambridge, which was back then a well-renowned company in chemical safety. So I joined them, worked for them for about 10 years. Then in '87, I started BlazeTech. And when I did that, many of my colleagues said, you're leaving Arthur D. Little, the international firm, to go start your own? I said, well, I'm doing it. Well, as it turns out, ADL went bankrupt quite a few years back, while BlazeTech is still going strong. Okay, so if you comment on consulting in safety, this can be done at various levels. At the plant level, and that's basically an audit function for compliance with rules and regulations, or evaluation of new systems. And that could be very exciting in the sense that I was involved in evaluating major subway system, as well as the channel between France and England during its design phase. Got to even attend hearings at the House of Lords in that connection. Very exciting. Now, the important thing, if you work on the plant level, is to report to the plant manager. If you're reporting to anyone in between, it could get very sticky, because the person, if he doesn't have the authority to stop operation if needed, then you will get a lot of pushback, and just things won't work well. So that's kind of my suggestion. Now, the other is to work at the corporate level. And you might recall that in 1982, the Johns Manville Company went bankrupt because asbestos was found to produce cancer. many CEOs then started to ask questions about potential liability with their products that could bankrupt their companies. So, for example, I was asked about whether a particular dust will produce cancer. And I had no idea, talking to the CEO. And I'd say, well, you have to plan a research program, etc. Except first, he didn't want to hear about that. He didn't want to spend any money. And in addition, he didn't want any record of our discussion. I kind of didn't like that. And I decided to really do R&D. You have to move to a different level where you're getting essentially funding from the government, because the government do sponsor R&D contract. And that's what I selected to do at BlazeTech. So now I'm going to talk about a couple of examples. The first is the vulnerability of aircraft fuel tanks to fire and explosion. That project was funded by the FAA, prompted by the Sioux City, Iowa accident, if you remember, where it killed quite a few people. It was not a fire and explosion of the fuel tank, but it raised the issue. Could it happen? And that's what we studied. And then before we finish our study, there was that TWA 800 accident, which killed 230 people, everybody on board. Now, if you recall, this happened July 96 on a very hot day. The aircraft sat on the tarmac for 2.5 hours. And to keep the cabin cool, the HVAC was working full blast. The plane took off. 12 minutes after takeoff, there was a mid-air collision. And over the Atlantic, the NTSB spent about $20 million to investigate this accident. Of course, it had to go down in the ocean and pick up all the pieces. And I don't know if you could see all the wreckage that they were trying to reconstruct. Some of our pictures are hiding that in my screen. You may want to reduce our photos if possible. Thank you, Teresa. I'd like to show you a videotape where I got interviewed by Dan Rather, who you might remember from CBS.
Good evening. TWA Flight 800 is holding on to its secret. 5 months and 2 days after that horrific crash that took 230 lives, the most basic question is still unanswered. Why? This much we know. The center fuel tank exploded. But what supplied the spark? Was it a bomb, a missile, or a catastrophic accident? So tonight, our focus, TWA Flight 800, fact and fiction. We begin with a hard look at the new leading theory, mechanical failure. You're about to meet one scientist who warned about the risks of fuel tank explosions 6 months before this terrible crash.
For the last 2 years, we've been saying it can happen.
But scientist Albert Moussa says no one paid much attention.
Explosions of various kinds.
It was 2 years ago that Moussa was commissioned by the Federal Aviation Administration to investigate fuel tank explosions.
What we see here is an explosion inside a simulation of a fuel tank. It's an empty tank, basically, except for the vapors.
His discovery? The risk of an explosion in a nearly empty tank is far greater than previously thought. Now, what was the reaction after you said this, after you made your report? What happened?
Well, some people thought it's not going to happen. It's not correct. People told me after TWA, well, you're right, things can explode in the air.
Someone in the government said to you, well, you may be right, or you are right?
Basically.
On that interview, first, as engineers, we are not prepared for an interview like that. And when I got the call from CBS, I called the FAA and I said, shall I respond? And their answer was, well, let your HR department or the PR department handle that. Well, I had no PR department. And frankly, if I had one, I wouldn't be sure I want to give it to them because they could mess up the answers. So I decided I better talk and stick to the facts. And Dan Rather was very good about that. He just asked about the fact. I had also an interview with the BBC who were actually very vicious about trying to extract names from me. Who did you talk to in the government at Boeing, etc.? And I would say, no, no, no. And they keep asking, etc. Anyways, so you can handle an interview. And if you stick to the facts, then it's better than not speaking and letting maybe some charlatan describe what they want. All right, so now what was the theory? What had I kind of warned people about? To explain that, I want to define a term, the flash point of a fuel, which is the lowest fuel temperature that can, at which the fuel can ignite by a spark. The flash point is tabulated in various handbooks, typically for various fuels and typically at STP. There is no effect of altitude. That is ignored, and particularly because the people doing this work tend to be chemical engineers. And chemical engineers don't think like aerospace or mechanical about altitude coming in. So how does altitude come in? If you look at the plot below, what I'm showing is pressure in the tank as a function of altitude. And there are two components to the pressure. The vapor pressure of the fuel is the part in blue, and that's governed by the temperature of the fuel. And the other part is the air. And you could see that at ground level, there's lots of air, so you're not flammable. And your temperature is below the flash point. When you go up in altitude, then basically air, well, gases leave the fuel tank to stabilize the pressure across the tank. But the fuel vapor pressure is maintained because the temperature is the same of the fuel. So you keep going up, and essentially you have less air and the same fuel, so you're becoming richer, and ultimately you become explosive or flammable. So when the guy told me we were operating below the flash point right here, yes, that was correct. But when you go up in altitude, then you are not. Or maybe the flash point ought to be revised, and then things can go wrong. Let me just give you an idea of the center wing tank in a 747. You could see that up here. And that is a huge reservoir between the two wings, and it's under the cabin. It's actually part of the structure of the aircraft. And it's big. It's like maybe a one-bedroom apartment divided into various compartments. And here I am standing in the dry bay ahead of the fuel area. And you could see here is a kind of the manhole through which you can go in, and you could see it in the diagram that. Now, obviously, if you fail that, then you affect the spar, you affect the structure of the plane, and the plane can be brought down. In this context, we developed a software called BlazeTech. And the software essentially answered the following question. For an aircraft and a particular fuel tank and a flight profile, is the ullage flammable? And when is it flammable? And how much vapors are flammable? And if it ignites, how fast will it burn? And will the combustion overpressure inside the tank be high enough to fail the tank? Now, I want to show you a little bit of technical stuff because that's what we do at BlazeTech. That software had two main components, a thermodynamic component that basically did a heat and mass transfer on the fuel and the ullage space. The ullage space is that vapor space above the fuel in a tank. And of course, because the temperature of fuel can change, the amount of vapors in the ullage can change. And because you're going up and down in your flight profile, gases can leave the tank or air can come in, and that will change the composition. So we developed a model that tracked that to tell you how big is the ullage as a function of time, the composition, is it flammable or not. Then we had a combustion model here on the left, and you could see a picture of a real flame, which we simulated by essentially a surface, a flame front, if you want, that converts unburned gases into burned gases. I guess that moved very quickly, but anyways, got to be careful with Zoom and all that. So on this slide here, we show the prediction of the model with NTSB test data. The test data were done on a quarter scale tank. That was a major national program. You can see here the pressure as a function of time at 3 different temperatures of the fuel. So at 40 degrees C, you see that when ignition happens, you're starting at essentially a little below ambient pressure, below normal pressure, because you're starting at an altitude of, it was about 30,000 feet when the accident happened. And then the pressure started to rise as you combust, and then ultimately you run out of vapors. Oops. You run out of vapors, and then it's a cool down. I'm going to avoid using that that pointer, which caused problem here. As you raise the temperature, you can see that you're moving from the orange to the violet to the blue line. Blue line is higher temperature. And as you raise the temperature, there's more fuel vapor. So you burn to a higher pressure and you burn faster. And then of course, once you complete combustion, the pressure peaks and then you have a cool down. The data point shows what the NTSB collected, and the curves show our model, which tracks the data pretty well. Thereby, we have essentially validated our model, which is very important in this business. Of course, look at the time over which ignition happened. Ignition and even complete combustion happened. For the highest temperature, it was 1/4 of a second. Now, that's also a quarter scale tank, so a full scale would be longer, but still, things happen very fast. Now, I'd like to tell you about some historical development to mitigate fuel tank ignition. Such ignition happened over the last 60 years or so. This plot shows the various instances of ignition, all these little triangles at the bottom at different times, ignition inside a fuel tank, and it happened due to the various reasons: lightning, a bomb, wiring, electrostatic problem, etc. Now, if you look at the first curve, that cumulative tank, this is a cumulative fuel tank incident that produced a hull loss, complete loss of the aircraft per million departure. And it drops very significantly, yet it doesn't go to zero. While of course the annual departure is going up. And the interesting part here is if you're a statistician, you say, well, there's so few accidents, the rate is so low that you've reached the noise level. Can't do much about it. It's gonna always happen. Engineers don't think that way. Rather, for every incident, there have been a study that decided what happened and how can we protect against that. So the incident is not repeated, but then of course something else happens. Now, I want to tell you a little bit about the development of the historical development of this business. In the 60s, the aircraft industry decided to switch from Jet B to Jet A. And that reduced the frequency of accidents significantly because Jet A has a much higher flash point than Jet B. So it's fundamentally a safer fuel. And that was great. But then for years, accidents still happened. And for about a 40-year period, all the work has been focused on reducing the potential for ignition inside the tank. And then ultimately, much later, there have been 3 major accidents involving the same kind of explosion like TW800, except the plane was on the ground. So the damage was much less severe, yet several people died who were in the plane then. And that forced essentially the airline and the FAA to change their position from working on fuel, on the ignition sources, to changing the environment in the tank by inerting it. So if you look at that period from 60 to 2000 or so, which are hidden by the pictures of us here, you see that initially the work was on the fuel. Then in the middle, for 40 years, work on ignition sources, and finally work on the air in the tank. And that kind of gives you the fire triangle between fuel, air, and heat source. But after TW800, it took 10 years for the FAA and the Boeing to decide that they should inert the fuel tank. And that is what's happening today. And by the way, 10 years after a major accident is not unreal in the aircraft business, because changes are very difficult to come by. Okay, I will skip some of the details for the sake of time. Now, Teresa asked me, are we doing anything about COVID-19? Well, not really, but I couldn't resist to show that just for fun. All right, next I move on to example number 2, the atmospheric dispersion of reacting agent. It's a model we developed called ADORA. It was prompted by the demilitarization of explosive and propellant, which has happened after the end of the Cold War. We had tons, thousands of tons of explosive and propellant that needed to be destroyed. And that was done by open burn and open detonation. And of course, DOD wanted to calculate what kind of emission products to satisfy the environmental consideration. So we did that for that purpose, and we developed a model that calculates the plume size, and you can see that in the picture here, as well as what are the products that are produced and how far do they go. So it was mainly for environmental consideration, but it was also very relevant to safety. Now let me show you a case of a detonation that happened in a depot in the Ukraine.
Ой, ё-моё! Ой-ой-ой! Сейчас придет волна! Нихера себе! Боже мой! Дом дрожит! Дом дрожит! Ой-ой-ой! Ой-ой-ой! Что же это такое? Это бомбануло! Ракеты летят в разные стороны.
This, we developed a model of a fireball. On the left here is test data done at White Sand National Lab, 150 pounds of liquid hydrogen, liquid oxygen fireball. It was kind of to simulate what would happen in the shuttle, if the shuttle were to come back and crash on the ground. And then if you look at the left side, we had our model prediction and compare that to accident data, the test you just saw, as well as real accident involving different propellant, RP1 LOX, various UDMH and ammonium nitrate. The bottom scale is the release of the chemical energy over 8 orders of magnitude. And the solid point is our prediction. The open circles are all these data we could collect. Obviously, these are very difficult data to obtain. And you could see the big scatter in the data. And our model predicts the average pretty well. So we were very happy with that model. In addition, what our model does is predict not only the final event, but also the intermediate product during the explosion. So here, for example, is the concentration produced as a function of time. And time is a very short time, as you can see, fraction of a second, for a magnesium Teflon flare. And obviously, you start with magnesium Teflon, and as time goes on, you're producing other species that can form and then disappear, and some remain. And the key point was really, what are the final product, which is the magnesium oxide and the magnesium fluoride. And then we can calculate that, and then you could see that over time, much later, the curve, the slopes becomes very constant, and they're dropping, and this is basically because the plume is being diluted. All these events of interest of combustion that happen early on are over with. And that also reminds me of the famous quotation that the solution to pollution is dilution. And here you can see that dilution, but to get the dilution properly, you have to know what are the products. And most people didn't know, if you release magnesium and Teflon in the flare, which product and in what concentration should you worry about? Should you worry about MgO or MgO2, etc.? So we answered that. We also found out that our model can handle moisture reactive chemicals. These are products that contain chlorine, fluorine, which is very reactive with moisture in the air. And historically, these gases are denser than air. So when they're released, they spread as a dense gas. This is in the top schematic. However, if you allow them to interact with moisture as they spread, and of course, as they spread, they're pulling in air, which has moisture, which release heat, and the heat expands the cloud rises, moves, pulls in more air, etc. So you can track the combustion part. And you could see that the photograph on the right also shows a cloud that is rising. So we did that, and we did several calculations for extremely reactive mixtures that had no model before. Presently, we're working on something else which derives from really that videotape you saw, which is called the cookoff of explosive. If you have a depot of munition, the big concern is if there is heating for various reasons, perhaps the ambient temperature went up or some external fire, etc. Could you cook off the explosion? the explosives. And if they cook off, you have this phenomenon you've seen before. And you could have what's called a fast cook-off or a slow cook-off. Now, the fast cook-off is on the right. If you're heating, normally heating happens from the outside. So if you heat from the outside, you develop temperature gradient as illustrated in this picture. And the gradient kind of develop as what the axis here is the radial distance from the center of the explosive out radially. So heat penetrates in and eventually you get ignition. Now, if you do that heating at a much slower rate, then the temperature profile is very uniform, and then it ignites inside. And once it ignites inside, everything ignites as opposed to the surface ignite, and then you have kind of a slower ignition as you proceed in. So the second one is much more reactive. The one on the left, the slow cook-off, unlike its name, is a lot more reactive, and you'd see that the fragments are very small and they go a long distance. While, I don't know, can I move our pictures out of the way? Yes, I can. Well, while you see
what the participants see is based on my computer, so don't worry about it, Albert.
Okay, so they can see it anyways? All right, great.
Yes, the view is good.
So you could see that on the right, the vessel that contained the explosive breaks up in a few small pieces, unlike the one on the left. So the left is much more reactive than the right. Essentially, things happen much faster, and the heat release is much higher because you involve everything at the same time, while in the other case, you involve them sequentially, and you may not involve all of them because once the casing fragments, then the pressure drops and the reaction rate goes down. So we are developing a model that sorts out between this case and that case. And the model is also useful to tell you the effective heating rate. So you could see that if you have slow heating rate, you're on the left, and as you increase your heating rate, it moves to the right. So for some mixture of heating rate, you could be somewhere in between. Also, an important point is how to scale this problem. For a fixed heating rate, the small vessel or small munition can behave like a slow cook-off, and then as you increase the size, it will behave like a large cook-off. And the reason, very simply, is a large one will develop more temperature gradient than the small one. So that kind of gave us a strategy as to how you can scale, and that's very important in testing because you cannot afford to test the full scale. Okay, now I would like to speak about a few general things which are not technical, but it's part of my journey, and I was told that is of interest to the audience, and certainly would have been to my interest to me when I started. So what are the key requirements for starting a consulting practice? The first is to become a subject matter expert. They call that SMEs. And that you can learn at MIT. And upon finishing my PhD, I was an expert in fire research. But that alone is not enough. You have to develop some experience, which give you credibility that you can do things, practical things, contact, and some business sense. And also, it helps to work in an area that complements your clients. So you're not competing with them. For example, if their heart of their work is on engine combustion, try to consult in that is very difficult. Yeah, you could do it as a faculty because you're doing it part-time, but to do it full-time, you can't because they want that knowledge in-house. On the other hand, if you're doing complementary work, like in safety, environment, energy, and there are others, then there's space for you. And of course, if the area is hot, then you're better off. And I had to move with areas to track the money, of course, which is important. The advantage of starting consulting practice is a low startup cost compared to the classical high-tech product type companies. The other advantage is diversity in tasks. That, if you like to work on different problems, that is just great for you, so to speak. But the disadvantage is you may not know the final outcome because you give them advice that may or may not follow it. And then another advantage is you can walk away from bad situations or bad clients. The disadvantage, of course, is slow growth. However, it can be very profitable. And if you grow, another advantage is how to establish a culture for your company. And if you're starting a company from scratch, that culture is very important because everybody comes in with their own ideas. Another obviously disadvantage is the insecurity about the next job. So as closure, consulting exposed me to many industries over the years. I worked in oil and gas, aerospace, energy, fire suppression, environmental assessment, and transportation system, many things I don't even remember. And I was like a kid in a candy store. Every time I started in an industry, I wanted to know more. And I learned a lot about it. And that really gave me a lot of satisfaction that I would not trade off for anything. Over time, BlazeTech morphed into a contract R&D company. And basically, presently, we have a cadre of about 8 people, including 3 PhDs and a network of consultants. We are equivalent to the R&D department of a medium-sized business. I know significant-sized business, 10 times, 20 times bigger than us, and their R&D department is minuscule compared to what we do. And we've worked on many areas of national importance. Our focus presently is in aerospace and defense, and we work mainly in what we've coined to be environmental safety, safety and environment kind of coupled together. And we've developed several software and hardware, and we're trying to sell them as product, but that's kind of a very difficult thing. But the good thing is we develop them mainly on client money. And actually, when we try to market them, we lose money. So balancing these two, it's a very important thing. Finally, we have an opening for someone to help us model this combustion detonation that I just described earlier. So if someone of you is interested, to let me know. Thank you for listening. I'd be happy to take any questions.
Albert, I send you both the physical and the virtual thank you and congratulations. That's a wonderful history and a wonderful set of work. Participants, please enter your questions into the Q&A and I'll direct them towards Albert. But let me get started with a question that may be on people's minds. You can't look any place nowadays without being confronted with data or big data. In the consulting business, in particular in the areas that you're applying, there's a wealth of historical data, but what are you seeing as the trends and how has your business changed with this increase in what's possible with data and machine learning, and is that impacting you at all? Is it a trend?
Well, actually, we have a small internal project to do machine learning and AI to extract precursor out of accidents to help prevent accident in the future. And we'll see how that works. Machine learning is not quite designed for that, but we're trying to see how we could modify it to do it. So we try to go with the blow, so to speak, and use new tools. And that's one example. I can mention many others if you want, or else we can handle other questions. I've lost you.
Please, participants, if you can enter your questions into the Q&A. I have a direct chat here from one of the participants. I think the question is related to your slide on the comparison between sort of a product or a consulting company and sort of maybe a product-oriented company. The question is, how do you go about finding the next job? You're doing your current consulting activity, and I think alluding to is you're distracted from trying to go find that next connection. How do you balance that? You're finding that next thing and executing on what you're doing now.
It's a very difficult balance. So the question is right on. But in my mind, the most important part is to excel in the job you're doing. Because you don't advertise for consulting. It's mainly a word of mouth. People see what you've done and they call you or they refer you. So do well in what you're doing, even sometimes at the sacrifice of chasing new jobs. But you still have to sacrifice. So it's a tough road. It's not an easy thing. You have to enjoy it. Then the journey is really the excitement as opposed to other things.
Very good. Thank you for that. You mentioned there's another question you directly chatted to me, and please, participants, direct chat is fine. Q&A is also fine. The software tools that you have developed as part of your business, do you view those as things that you then could sell as product, or are those things that you remain and keep internal as proprietary that gives you a leverage and an opportunity over other potential consultants or others?
We've done both, but the latter actually we found it to be more viable, because these are very complex problems, and to sell it as a kind of standalone independent software takes a lot of work, because you have to anticipate so many things, and then you have to also anticipate how people can misuse it and come back to you. As a matter of fact, in some cases, well, we were offering, we would sell it, or we would run it in-house for you as a SaaS model. And actually, we were doing SaaS in the early 90s, before SaaS was popular. And the way we did it was we had a worksheet that people have to fill out about their product, how big, what can be released, etc. They send us that, and then we calculate the plume and the toxic signature, and we fax them back the profiles, and they use that in their assessment. And that was done by fax machine. Now the web-based. In one case, I remember the client wanted to buy our software, but I didn't think he knew enough, and I was worried about him misusing. So what I did was I raised the cost of the software and lowered our SaaS price. So he comes to SaaS, and he did. And then we gave him the answer because we know how to use the software, and we couldn't take the chance of letting him use it. And it worked out. So there was no backlash.
Very good. Albert, thank you very much. I sent another physical and virtual clapping here, and participants, Albert has been kindly offering to let you reach out to him directly, so his email address is here. So please reach out to him directly with further questions, and that applies to both people on the call now live and the pre-recorded. So Albert, again, thank you very much. Before we leave for the day, if I could ask Teresa to bring up our exit slide. As everybody knows, this is our weekly seminar series to connect our students, our faculty, and our external partners and alumni with each other to be able to continue to build community and celebrate the phenomenal work that everybody is doing in these unique times. Next week, same time, same channel, we'll bring to you Professor Vivek Sudhir, talking about the birth and death of a single quantum of vibration. So a wide diversity of topics and experiences you're gaining by following this on a weekly basis. So I thank everybody. I thank the participants for sharing your time with us today. I thank Albert again. Thank you for sharing your voyage, your journey, and the exciting work that you're doing. And if you would like to recommend yourself or others, faculty or external companies or the people that you're working with, please drop us a line and let us know. And with that, please have a good remainder of your day. Stay safe, and see you next week. Again, Albert, thank you. And
thank you, Albert. Thank you, everyone, for joining.
Thank you.
Have a good day.
Yeah, you too. Bye-bye.
Bye.
Bye.